starting the live.
That's great. Oh, I think Prontic just rejoined.
Can you hear me?
Mm-hmm. Welcome back.
Thank you. Double checking the video. Everything fine?
I think so. Yeah. There was some background noise. Can you just speak one more time?
Can you hear me now?
I think it's a little muffled, but I think it should be okay. Keep
Let me join again.
No. I think it's okay now, Prontic. I think it was just like
Okay.
when you got started. So great. Well, welcome everyone to our attendees. Our webinar attendees will start in just a few minutes here. Welcome everyone. We'll start the webinar at 1 p.m. Hi there, Kara. Good to see you.
Good afternoon. Can you hear me all right?
We can hear you all right and see you all right. I'm
Great.
just going to change your name to
Oh,
include.
I was going to do that for you. Okay.
No,
You-
I'm quick on
you.
the draw. Yep. Thanks
I
for
ha-
being here. Yeah.
Sure. I have a group that I always take that off for, and then I need to put it back on when I use Zoom again.
Yes, you're fine. You're fine. Well, thanks for being here, and we'll get going in a few moments.
Sounds good. Thank you.
Welcome to our participants. We'll start the meeting in about 2 minutes. Welcome all participants. Thank you for being here. We'll start the meeting in a minute or two. Welcome, everyone. We'll get started in about a minute. We know this is just after the lunch hour, so waiting for folks to gather. Thank you for being here and happy belated Earth Day to everyone. All right, well, in the interest in keeping us to our 90 minutes together and respecting your time, let's officially get started. My name is Sophie Glass, and I'm a facilitator with Triangle Associates, and I'll be guiding us through today's webinar. Next slide, please, Jack. So in terms of your Zoom functionalities as a participant, you'll be able to see messages from the host. So we'll be providing some links to you all during the public comment period. You'll be able to raise your hand, and we look forward to hearing from you. And throughout the meeting, the Q&A function will be going, so drop questions in there, and anything that we can or PSE can answer today on the spot, they will, and anything else that they can't answer on the spot, they'll respond to in the feedback report. And for those of you who are helped with closed captionings, those are turned on. So next slide. So my requests, just, be constructive, courteous. I'm going to try to keep us moving today. We know acronyms are a part of this work, but, this is a public-facing webinar. This is PSE's effort to engage the broader community in these important resource planning conversations. In the appendix to the slide deck today, there is a list of acronyms, but let's try to avoid them. Use the feedback form, or you can always email irp@pse.com if there's anything else you want to share. And our focus today really is on these kind of emerging energy storage technologies, so let's focus on those. Thank you, Emily, for dropping the feedback form in the link. All right, and at the end, we are looking forward to hearing from you all in public comments. Next slide. All right, the safety moment today, really keeping in line with the weather, is about outdoor hiking safety. So do your research, know about the trail, weather, etc. Pack a map, bring extra food and water. If your pets are allowed, keep them on a leash and don't touch wildlife and plants. And if you're me, make sure you leave enough time to go and come back while it's still light out. I've made that mistake many times. Next slide. So today's speakers will include some familiar faces from PSE: Kara Durbin, who's the Director of Clean Energy Strategy; Elizabeth Hosner, who's the Manager of Resource Planning and Analysis; and also on the PSE side is Malcolm McCulloch, who's the Manager of New Products and Services. From Black and Veatch, we have two presenters, Prantik Saha as well as Mike Eddington. Next slide. Let's see. There we are. So here's our agenda. I'll just ask that Emily, in the public chat, can you add the link to the agenda and to the full slide deck so participants can follow along at home. But we'll start with just recapping some recent engagement and public feedback, turn to Elizabeth to tee us up about this energy storage concept, spend most of the meeting hearing from Prantik and Mike about energy storage technologies. And then I know many of you are interested in the kind of vehicle to grid or vehicle to everything concept. So we're going to save time for that towards the end of the meeting and wrap with public comment. Next slide, please. So with that, I'm going to turn it over to Kara to share some information, but also pose some questions to you that you can think about today throughout today's presentation. So please, Kara, go ahead.
Thanks, Sophie. I appreciate it. You can go to the next slide. Thanks, everyone, for joining us today. I'm just going to talk a little bit about where we've been and where we're headed on this emerging resources engagement effort. And so this first slide is really just for your reference around the IAP2 spectrum and how we think about public participation moving as a spectrum from left to right. And so in this series of both technical conversations and public webinars, we've been ranging across informed, consultant, involved, which is the box that you see here. And I think that'll make a little bit more sense once we get to the next slide. So if we go to the next slide, we'll just talk through a little bit of where we've been and where we're headed in wrapping up this emerging tech series this afternoon. So we've been asking for feedback and really thinking about how emerging resources will be a part of this resource planning cycle for almost a year now. And we started this off back in June of last year. And I can remember like meeting with some of my colleagues and thinking about like, well, how do we frame this survey and what kinds of questions do we ask? Really looking for members of the public to participate in a survey to tell us what sort of emerging resources we should be studying in this next IRP cycle, what different battery, durations we should be thinking about, what other resources in terms of small modular nuclear and others should we have on the table to consider. And so that kicked off in June of last year. And then the results of that survey informed as we brought to the public kind of our a conversation around, well, okay, what should our overall work plan for this IRP cycle look like? And we had a meeting in September where really we're asking for feedback on, are these the right topics? Are there other topics you're interested in? And that ultimately, those conversations and the feedback we received informed the work plan that we filed in September of last year. Then we moved forward in starting this series of public webinars that looked and felt a little bit differently than how we did things the last IRP cycle. And in December, we hosted our first emerging resources webinar on hydrogen. And then starting the new year in January, we met with our relatively new then technical resource planning advisory group to begin discussing our emerging resources assessment, like what we had learned from that survey, and really get feedback and ask for more feedback on what we should be studying in this IRP cycle. Then fast forward to February, we held our emerging resources webinar on small modular nuclear. For those of you that attended, it was a really lively public webinar. Lots of questions were coming in, many of which we answered in the webinar, many of which we answered in the feedback report that we prepared afterwards. So we were really, it was a really good dialogue around how we're thinking about small modular nuclear as we look at a variety of emerging resources that may be available in the coming years to meet our needs. And then last month in March, we specifically, we met with our technical advisory group again to then continue the conversation around emerging resources, diving into some more detail on a number of different technologies. It was lots of nitty-gritty details, but I also think it was, for those RPEG members, it was some of the information that they were looking for. And then fast forward to today, we're really picking up a conversation with you on energy storage in particular. So all in all, we've had a number of opportunities over the past year. We look forward to some more conversation today around energy storage, and we're always open to feedback. And so we have a couple questions on the next slide that I want to tee up for you to consider. And as the webinar progresses, perhaps you can either put it in the Q&A or make public comment at the end. So if we could go to the next slide, I'll just briefly cover those. So the first one is, what really trying to get a real sense of what risks do you see, or what benefits or rewards do you see for energy storage that PSE should keep in mind? And then the second question is really, we're interested in whether you have some examples in mind of energy storage projects you've read about, you have experience with at other utilities that you think are really particularly good ones for PSE to consider. We obviously look at what other utilities are doing and try to stay up to date on the research and the pilots that are happening. But we're always curious to know, where do you think there are leaders in this space, and what do you think we should be considering that's important? So lots of opportunities to do that. The feedback form will be available after the meeting. We of course have public comment at the end. There's the Q&A box, and our email box is always an option too. So with that, Sophie, I think that's it for me.
Yeah.
So thank you.
Thank you so much, Kara. So in your chat box, we just pasted the questions so that you can refer to them as we move along. As Kara mentioned, submit some of your thoughts via the Q&A box, either public comment at the end or store up your brilliant ideas for that feedback form. I want to acknowledge that we do have a phone participant, and so as different speakers move along, just make sure you explain what's on the screen rather than just only relying on visuals. So we're going to move along to the next slide. All right, Elizabeth, can you come on camera and just tee up our conversation today about energy storage?
Yeah. My name is Elizabeth Hosser. I'm the Manager Resource Planning here at PSE. And I'll just be kind of going through an overview of what is energy storage and leading into the conversation with Black & Veatch with some of the different technologies. I think next slide, please. So for resource planning for the IRP, we go through a few different processes of planning. So right now we're in the planning stages, and really as part of the planning stage, we're trying to establish our resource needs, looking at demand growth into the future, what might happen. We're trying to assess how different resources can meet that demand into the future, when we might need resources, and the sizing of those resources. And that's some of the important pieces we take away from this planning stage. And to just point out, we're in the planning stage. We're not in an acquisition stage right now. The acquisition process is a different piece, and that comes after we do planning. So in this planning stage, we are looking at what is generic resources. And what we mean by generic resources is we're really trying to evaluate sizing of the resources, when resources need to come in, and what types of resources. Do we need a type of peaking resources or some baseload resources for meeting energy needs, renewable resources for meeting the clean energy requirements? And so we're just trying to look at those assessments, different types of resources. And so what we've created is these generic resources, and they're really intended to be placeholder resources, just to get the sizing, timing, and when these resources should be coming in. And what comes out of an IRP is not a shopping list of what we'll be doing. We are still keeping our options open. We are still looking at what's out there. We'll still be going through a full acquisition process and really evaluating all resource options as part of that process once this planning stage is done. So as I mentioned, like these are really just placeholder resources, and we're just trying to get ideas of what's out there. What are our options? What can we be looking at? And as part of these emerging technology assessments, some of these resources may not be available today. So we might not have some commercially available resources today, which we are also looking at for current needs. But we're also trying to look at into the future planning. When might some resources be coming in? How should we be planning for that as well? And so as part of this assessment, we've gone through various stages, looking at these different types of technologies. We're looking at a combination of currently commercially available resources, along with some emerging technologies that may come in into the future for meeting needs. So really today's objective is to look at energy storage, and that's one of the types of resources we're looking at. We've had different webinars looking at the different resource options. This one's really focused on energy storage as one of those options. Next slide, please. So the question is, what is energy storage? That's coming in as one of the resource options. And in looking at energy storage, these are what can be called like energy limited, or essentially like neutral resources. They don't specifically produce energy themselves. What it is when you have excess energy on the system at specific hours, you can put them into storage, and then you can discharge that energy at a later time when it's needed. So this can usually go will go out a couple hours. So we have various durations of batteries, from like a shorter duration from like 2 to 4 hours, or longer durations depending on what might be needed. So that's what we're trying to evaluate, is the sizing of these resources, and when and how we can call upon it. There's lots of different technologies and how the storage will work. That's where Black & Veatch will be coming in, is explaining how the storage works, how we can work with that to make sure that we can move energy from different hours of the day to when we have excess to when the energy might be needed. So the energy storage can play an important role in how we're assessing these needs and making sure demands are met as well. I think next slide, please. So some of the feedback we did receive around storage coming from the 23 progress report we filed, we did get feedback in that. We're trying to bring some of that feedback back to the 25 IRP and some various feedback we've been receiving along the way. Being that we want to model looking at new emerging technologies and modeling different battery configurations. And so that's really where Black & Veatch has come in. We've asked them to put together this emerging technology assessment. Really, a lot of it's focused on energy storage, because energy storage, there's a lot of new technologies coming in. And so this is where we're trying to evaluate all these different technologies, all these different options, how some things might fit, where we're going with these, and just looking at some of the sizing that could happen as well. Some of the other feedback we've received is exploring vehicle to grid. So this is using the batteries from electric vehicles as a potential storage option as well. And so we do have Malcolm coming in to talk about those options with looking at that as well. I think next slide. I think I have two more slides. Okay. And so when we look at our options, really what's coming out of this is we assessed all of the emerging technologies, and they've been assigned this what is technology readiness level, or TRL, as we've shortened it. And so each resource is given a different level. This is kind of based off of a NASA technology readiness level system. And so when we looked at what we should be including as some options for this IRP, this, like I said, this is not a full comprehensive list. What we're trying to do is just kind of narrow down the list for some possible placeholder resources. And so we really want to focus on resources that were at a level 7 or above. And what that means is level 9 is it's currently commercially available. It's in operations. You can get these resources. They're at full scale. Level 7 being that they've got a demonstration project going. Maybe they're looking at trying to get a full-scale project setting up for the next stage. And so it's resources going from demonstration projects all the way up to their full-scale, ready to go. So this is kind of the levels we were looking at for evaluations for this 25 IRP. Next slide. I think this will be my last. So what we did is there's a lot of technologies out there. And so we broke this down because what we're trying to do is really looking at storage in terms of its size. What sizing would best fit PSE's needs and the demand? And so we kind of broke down the technologies into what we're calling short duration. That's anything that would discharge the storage at 2 to 8 hours at a time. So if you were to put energy into the storage, you could get 2 hours, 4 hours, 6 hours, or 8 hours duration to discharge out the storage at different times. And then we've got the categories under what is medium duration. This is the 8 to 24 hours, so up to 1 day worth of storage and discharge of the energy. And then the longer duration. So these are the multi-day storage technologies where it can discharge the energies over multiple days. And so this will be for longer duration needs. Whereas the shorter duration would be just more essentially like very peak needs during a day. You may see higher demand. You can discharge energy for a couple hours versus longer duration will be over multiple days. And so I think this next piece will be transitioning over to Black & Veatch. And what they're going to go through is these different technologies that we've listed out. And so some of these technologies we have under the shorter duration, medium duration, and the longer duration storage. So we just did call out one piece, Black & Veatch. They will not be going through pumped hydro. So what we do have is we have a bunch of information through the 21 IRP, 23 progress report that we've done on pumped hydro storage modeling. We asked them to focus more on the other technologies so we can get more information on other technologies. So they'll be going through the other mechanical energy storage. So pump storage is a gravitational mechanical energy storage. So they'll be going through some of the other technologies and the different options that we've been looking at as well. And so what we've also highlighted is going through the list of the resources available, their technology readiness. We did make some draft decisions on like, where should we go? Which technology should we put in as the placeholder generic resource? So we kind of highlighted that in blue. We're also getting feedback on these technologies as well today.
Great. Thanks so much, Elizabeth. You can go to the next slide, please, Jack, while Black and Beach. Prontek and Mike, if you can come on camera for me, please. Excellent. And Prontek and Mike will have until 2:05, so that's 45 minutes for you all. And for our webinar participants today, please keep your questions and comments coming in via the Q&A, and we're going to pause after the low and then medium and then high duration storage just to kind of cluster your Q&A. So Prontek, please get us going.
Thank you, Sophie. Can you guys hear me properly? Okay, fantastic. So so we'll be talking about different energy storage technologies, and as people mentioned, it's divided by durations. So the first topic is the shorter duration energy storage systems that are between 2 to 8 hours. Next slide, please. Okay. So as I mentioned, 2 to 8 hours are being considered as the short duration energy storage for this project. And these energy storage technologies for this duration is most deployed as of today. So we have about close to 28 gigawatt hour of energy storage deployed globally. And they have the highest technology readiness level. So in terms of the TRL that Elizabeth showed, it's TRL 9. And we have a lot of commercial lithium-ion battery vendors that are available today. And we also, because of this high level of deployment and a lot of experience, the project risk is significantly low. Like, we know where things can go wrong and how to fix them if things go wrong. Now, for this case, what we studied is we basically studied two electrochemical battery storage technologies that are lithium-ion batteries and sodium-sulfur batteries for this duration. And we considered basically the different technical aspects of the batteries and also the safety concerns. Now, the first category in this duration is the lithium-ion battery, which all of us know very well. They have been deployed from microelectronics to large-scale energy storage systems. Technology is de-risked. We know them very well, and it's also evolving with time. For stationary energy storage applications, there are two types of lithium-ion chemistries that are deployed. One is called the NMC, or basically lithium nickel manganese cobalt oxide, and the other is lithium ferrous phosphate, or LFP. NMC used to be the chemistry that was used before. LFP came later, and LFP has some advantage over NMC in terms of cost, durability, and also, if you notice, there is no cobalt in LFP, which makes that the supply chain is more sustainable. The other category of technology, what we consider is sodium sulfur battery. It's a different technology than lithium-ion batteries, and in this battery, we only use molten sodium and molten sulfur, and they actually operate at very high temperature, about 300 degrees Celsius efficiently. And in this case, at this temperature, all the elements, sodium and sulfur, are in molten state. So that's why it's sometimes called molten sodium battery as well. Now, a question is usually asked: why would people use sodium sulfur battery if lithium-ion battery is already so popular and it's already so de-risked? Well, there are two answers to that. The first thing is it uses sodium and sulfur, so this battery doesn't contain many critical materials in its whole system, and also balance of plants. So it has a little bit of a supply chain advantage over lithium-ion batteries. And secondly, if there is a facility where there is waste heat, say a chemical plant, the waste heat from the chemical plant can be used to keep the battery temperature above 300 degrees Celsius. And in that case, the operational efficiency of the battery will be really, really high. So the OpEx will be low in that case. So these are the two battery chemistries that we consider. Next slide, please. So in terms of geological requirement, we really don't, these two just require flat land. They come as containerized systems, so you just put in the containers and you connect with the electrical balance of plants. The largest lithium-ion battery project, as far as we know, is actually in California, and it actually came into operation in January this year, late January this year. And it's a 3,200 plus megawatt hour of duration. It's coupled with solar. And the largest sodium sulfur battery today is that it is in UAE, which is above 100 megawatt, 6-hour duration project, and it's been operational since 2019. So both these technologies have been de-risked and been operational. So with this week, I'll stop and see if people have any questions.
What questions might you have for Prantik so far? Questions or comments? I'm not seeing any quite yet. I think when some of the less familiar technologies are presented, perhaps we'll get more questions. So next slide, Jack, and carry on, Prantik.
Sure. So this is the last slide for the short duration energy storage. So these are some of the safety concerns. So for lithium-ion battery, the biggest safety concern is a fire hazard that occurs due to thermal runaway. A thermal runaway is basically a situation. So when a battery usually, is in operation, you discharge it or charge it, it generates heat. There is a thermal cooling system, in place in the container that is used to control the temperature. If for some reason that doesn't occur, so the temperature just increases repeatedly, it's a runaway situation. And we have seen some, fire occurrences due to thermal runaway in lithium-ion batteries. One thing to note is that the LFP chemistry is definitely way less risky than NMC chemistry in terms of stationary storage, and that's why we are seeing a shift to LFP chemistry for stationary storage applications. And we are also seeing the companies are deploying a liquid-cooled system to prevent thermal runaway because it's more efficient than air-cooled system. However, if fire occurs, then we see that there are several toxic and flammable gases like hydrogen fluoride, ethylene, and many other organic gases that come out, hydrocarbon gases that come out. And electrolyte spill can also occur. So this is about the lithium-ion battery. For sodium sulfur battery, the fire is mostly caused by, if you remember, it has molten sulfur and molten sodium. And if they get exposed, these are highly reactive metals, they get oxidized very easily and they cause fire. And also because of their high reactive nature, they corrode the walls very fast, although there are R&D developments and we are seeing much better performance over recently in the last 2-3 years now. And also in case of a thermal runaway in a sodium sulfur battery, it is really difficult to lower the temperature because it's already at 300 degrees Celsius and highly reactive, and thermal runaway events are just go out of hand very quickly. So these are the major safety concerns for the lithium-ion and sodium sulfur batteries.
Thanks. Thank you, Prantik, for that. I'm not seeing any other questions in the queue quite yet. But as you know, participants, anytime a question arises, even if it's a few slides down the road, we can always go back. So let's keep moving. We can turn our attention to those medium duration options. So next slide, please, Jack. Okay, Mike, is this you now?
Yes, it is.
All right, take us away.
Good afternoon. So yes, the medium duration storage, it's looking to the 8 to 24-hour delivery periods. And I'll address the compressed air energy storage and mechanical energy storage options. So next slide. So with medium duration energy storage, what we're looking at is taking power from the grid to offset, taking power from the energy storage system and providing it to the grid during periods where renewable generation is low. Also, it can be used to shift energy from different times of day for different use. And it's not normally considered for frequency regulation. So the type of systems we looked at included compressed air energy storage. Pumped hydro energy storage was not evaluated by Black & Veatch in detail, as it already had been evaluated previously. mechanical energy storage, and then flow batteries. Next slide, please. With compressed air energy storage, what we have is a charging process that takes low-cost energy off the grid and uses it to compress air or other gases. Those compressed gases go to underground storage caverns or possibly above ground storage. Then during the discharge process, that compressed gas is released, it's heated, and then it expands across an expansion turbine. So some of the considerations in compressed air energy storage is the availability and design of the underground caverns that are associated with the air storage and the associated size and cost. In particular, if we're looking at above ground storage for a large facility. Plant sizes are typically considered in the 100 to 800 megawatt size. Within the compressed air energy storage are different subcategories, and they can be described as adiabatic, which takes the heat of compression. So as we compress the air, it warms up from that process and we store it. And then when we take the air from the cavern, it's cold. So we want to use that heat and heat the air prior to recovering the energy through expansion across the turbine. The diabatic compressed air energy storage does not save the heat of compression, but it heats the air that's coming from the cavern prior to expansion by burning something like a natural gas or possibly a hydrogen fuel could be used either in conventional combustion turbines, which provide exhaust heat, or through different stages of combustion ahead of the expansion turbines that drive the generators. And then a third primary type is the isothermal. And the idea there is to continuously remove the heat of compression, which makes the compression process more efficient, and then to reapply that heat continuously during the expansion process. It's something more of an idealized type cycle, but it does not require any combustion process similar to the adiabatic type does not. Next slide. For the case projects, one of the bigger consideration is the geologic requirements. So we have typically seen the two large operational case plants use salt caverns, and those are underground deposits of salt that have been solution mined to create a large cavity to which we can direct the compressed air. And we would call that as a technology readiness level of 9, since it's pretty well proven through plants that have been in operation since 1978 in Germany. We have a 290 megawatt unit there. And then in Alabama, we have a 110 megawatt unit that's been in service since 1991. So again, these are the kind that use natural gas firing to provide the heat prior to expansion. The next kind is the adiabatic and advanced adiabatic. And some of these provide more latitude in the type of geological requirement. So the underground storage can be done in a mined cavern. So if you have hard rock formations, such as in Washington State, those can be mined out, and then that is where the air would be stored. So we don't have to have a salt type cavern. The status of those advanced adiabatic type are the ones that store the compression heat. So we've seen a 60 megawatt 5-hour unit in China. And then a company called HydroStore has been developing a advanced case unit, and one of them is a 500 megawatt 8-hour unit that they're trying to develop in California. There's no strong requirement for geological caverns for isothermal, primarily because it's still in an early phase of development. So it's still generally considered as a small scale application in pilot and demonstration stage. So that's technology that's still in the works. Next slide, please.
No, Mike, I might actually break in and just make room for one question. We're doing fine on time. So a question here, yeah, I'll read it aloud for those on the phone. Both the lithium ion and sulfur sodium battery technologies will be useful. Just want to note that the safety concerns will make these harder to site within a community. I don't know if or how PSE factors that into an IRP, but it might affect some cost and efficiency metrics. Can be useful tools in a portfolio of diverse resources. Elizabeth, do you want to respond to that?
Sure. So what we do in the IRP is we are just trying to get sizing of resources, and we are looking at very general areas, like large areas, like in PSE's entire system of we just need something to fit this type of size of a resource. And so we're not necessarily going into the details of exactly where resources may go. That, again, will be going into an acquisition process. So as part of the IRP process, we're just really trying to identify the needs of resources, permitting, things like that, of where specifically resources can go. That would be the next step as we move into the acquisition process to actually start evaluating the resources.
Thank you, Elizabeth. Mike, how about you carry on, and we'll do another slide, and then we'll break for another question in a moment, but I want to keep you moving. So carry on, Mike.
Okay, great. So if we go to the next slide. This is a discussion on mechanical energy storage. So what we have then is a process where we're taking surplus energy off the grid, and it's using to drive that mechanical process to store energy, and then we release the stored energy to convert it back into electricity during our peak periods. What we had looked at with some further evaluation was liquid air energy storage and gravitational potential energy storage. So within that are some subcategories: flywheels, which are high-speed rotating disks that release the energy kinetically. We have consideration of hydraulic accumulators, which store energy by compressing a hydraulic fluid in a chamber. And then when the power is needed, that compressed fluid drives a hydraulic motor. And that hydraulic motor can be reversible to act both as the generator and the motor to compress the storage. Liquid air energy storage basically leverages the principle of air liquefaction and expansion to store and retrieve energy. The gravitational potential energy storage systems are pretty broad, but they include ideas like lifting heavy objects against gravity and then using that stored energy to drop the heavy object back down. And as you do that, you release the potential energy from that stored system, making electricity. Then other things like spring energy, think of winding your watch. You stored the energy and it's being released over time. Also kinetic energy storage with rail systems. So what you're doing is you have rail cars that you're accelerating along a track, and those have kinetic energy associated with them. So as you put on the brakes, you're converting that energy of the motion of the rail car into electricity. So you retrieve the energy through that process. So as mentioned, within mechanical energy storage is also pumped hydro, but that's not included in the Black & Veatch study.
Mike, I'll pause you here. And there was a
Mhm.
question about the compressed air energy storage from a few
Yep.
slides ago. So here's a question that if you don't know the answer now, we can come back to it. But there's a question about, have any of the existing installations of diabatic Ks, which is compressed air energy storage, that Black & Veatch
Mhm.
studied use fuels other than natural gas as a fuel source? If so, which fuel sources? Do you have thoughts on that
Yeah.
right now? Yeah.
Yeah, I sure do. So, yeah, as I mentioned, there's really only two large case units in service, and they both rely on natural gas as the source of heating. There's a lot of interest in trying to use cleaner fuels, so hydrogen's an important thought to consider, so that you don't release CO2 into the atmosphere. When we burn natural gas, we create CO2. So that's in the interest of being, decarbonization. That's not necessarily a favorable thing. So, yeah, right now there is no hydrogen fired or green fuel type fired Ks, but it would be something to definitely consider.
Great.
As I mentioned, some of them consider there's a process called Ks2, which has a gas turbine, and that gas turbine could burn hydrogen, for example.
Very good. Well, I think we can move along 10 more slides in about 20 minutes here. So you can keep focused on these mechanical options. Go ahead, Mike.
Okay. Yeah. So for mechanical energy storage, it's geologic requirements, really depend on, elevation differences for a lot of the technologies, or enough land area, for a rail system. So there are considerations. Obviously, the greater height difference between the maximum height of a gravity-based storage is really important. So when we look at liquid air energy storage, there's really not a concern other than having available space for it. So that's not it. It's a little more energy dense, let's say, than compressed air energy storage. So you can have a given amount of megawatt hours stored with liquid air in a smaller space than compressed air energy storage when you look at the entire system. The liquid air energy storage is being commercially offered, but not proven in a full commercial, 50 megawatt and larger build out yet. But it is being offered in 5 to 200 plus megawatt sizes. And there are some plants that are in various stages of construction or execution development for 50 megawatts in 6 hours in the UK, and a larger unit that would discharge 200 megawatts over 12 and a half hours. The gravity-based, as I said, it's pretty wide ranging of ideas and concepts. There are some that are being under construction. For example, there's a 5 megawatt unit that would have a 15-minute duration in Nevada that I've seen pictures showing, them developing the system. Then there's a 25 megawatt 4-hour energy storage system with energy vault. So the next slide. Yep. So for liquid air energy storage, as mentioned, it's a technology readiness level of 8. It what it does, it takes electricity and liquefies the air and stores it in an unpressurized vessel, heavily insulated. And then when it's needed, liquid air is warmed back up. That liquid air is vaporized again using the stored heat of compression and also any waste heat that might be available. So it really looks to be benefited from having a co-location where fairly low-grade waste heat is available to incorporate to improve the efficiencies, and can be offered for durations of 10 hours or more. So it's a fairly simple technology, well proven over time to the liquefaction process. It's scalable, it's flexible. As mentioned, it has a high energy density. Some of the challenges are you are storing and handling liquefied air, so it's at minus 321 degrees, for example. So it's pretty cold. So definitely some special considerations in design to handle that and to store it. But yeah, so the next slide, please. For the gravity storage, as mentioned, there's a whole host of different ways. The rail, people are designing systems that lift blocks up in the air. So it could be an entire system that lifts a series of blocks up in the air and kind of shuttles them across on a different floor. If you think of like a high-rise building, and you can store those large cement blocks and then store that energy until you want to retrieve it by moving the blocks back off and letting them down. So what you have is a motor which acts as the winch when it's lifting, and then when it's wanting to generate power, it also acts as the generator. So there are a lot of really interesting ideas for gravity energy storage. It makes a very large building for that. So that's something to think about. And then with the other ones, which are looking at going up a hill, for example, to run a series of carts or cars up and down the hill, they have a pretty big visual impact as well. So that's what I have to say on that.
Thanks, Mike. Is this the last? Oh, you still have flow batteries. Is that flow batteries you? Or
Nope,
switching over to
that's
Prontic? Okay, let's pause one more time to see while we just have you on camera, Mike. Any other questions, concerns, thoughts on these middle duration energy storage ideas so far? Okay, I see one popping up in the chat. Question here, has PSE considered, and maybe Meredith, how about you send this to live so that we can, other folks can see it first, and then I'll read it aloud. Okay. So the question is, has PSE considered any of the thermal storage batteries, hot bricks or sand, ice, etc., for customers who are looking for reliable heat or cooling? These are specialized applications, probably mostly for high density or industrial applications, but they seem like they're feasible for certain applications. Mike, any thoughts about those other kind of ideas?
Yeah, electric thermal energy storage is certainly another area of great interest and development. As you mentioned, what you do is you have electric heaters that are, let's say, heating a sand or a concrete or graphite or other storage medium. And then you can take the stored heat and perhaps make steam from it to reconvert it back into electricity when the peak demand is in greater need. So those are systems that have a high energy storage efficiency. The harder part is to have an efficient conversion of that thermal energy back into electricity. So does reduce the overall round trip efficiency of that process. But if you were looking at, and as the person commented, looking at heating and cooling, if you're looking at especially use of process steam or something like that, it's a very efficient way to store electricity when it's available, and use that to mitigate or offset other fuel needs.
Thanks, Mike. I'm not saying anything else for you right now, so you can take a breather, and Prontek, you're back up to talk about flow batteries. Go ahead.
Okay, can you hear me properly? Yeah. So flow batteries, again, so Mike talked about the mechanical energy storage systems, and now we are back to electrochemical systems again. So flow batteries, again, are electrochemical systems, and the primary difference between, say, the lithium-ion batteries or traditional batteries and flow batteries is that here there are two components. One is a power conversion stack or power production stack, and the other is the electrolyte containers where the energy is actually stored. So here the energy storage and power conversion happens or power production happens in two different physical systems. Now, it stores energy in the electrolytes, and based on the electrolytes, we have different types of flow batteries. The most popular and the most mature flow battery technology is the vanadium redox flow battery, where we use vanadium oxide as electrolyte component. We also have iron chloride flow battery, also zinc bromide flow battery, and a new class of flow battery that came recently, which is called the metal coordination complex flow batteries. Again, for this project, we compared different technical aspects of the flow batteries, the round trip efficiency and all those things. And also we will briefly touch upon the safety issues of different types of flow batteries. Next slide, please. So this slide shows you basically the deployment of different types of flow batteries. And as I mentioned, first of all, the geological requirement is same as the usual battery containers. It just needs a flat land. However, because those two things are separate, and like power conversion and the energy storage stacks are separate, they usually require large footprint. Larger in compared to lithium-ion. So the vanadium flow batteries are the most matured ones, and the biggest project is actually operational since 2022, and it's in Dalian in China. And they use a 4-hour system, although it's not really clear why, because it's more cost effective in longer duration. But that's the biggest operational project in the world. And we have, the scalability can be scaled from even less than a megawatt to hundreds of megawatts, depending on the space constraint, how much space available land you have. The iron flow battery, it's comparatively newer. Most of the projects we had so far are below the 10 megawatt scale. The biggest project is actually being under construction in Sacramento, which is a 200 megawatt 10-hour project. And to the best of our knowledge, it's about 10% complete. It could be a little bit more than that too. The technologies with less technology readiness level are zinc bromide and metal coordination complex. So they're kind of like TRL7, which means that basically their first phase of pilot projects are being constructed now. So for zinc bromide flow battery, we have a project in Southern California, which is 2 megawatt 10-hour project under construction. And the metal coordination complex battery, the biggest one under construction, is a 5 megawatt 8-hour system in Canada. And this is basically summarizes the different types of flow batteries, their TRL levels, and their deployment in different areas. Next slide, please. Okay, so in terms of flow battery, in flow batteries, their safety concerns are definitely much lower than what we discussed for lithium-ion and sodium sulfur batteries. So, for example, they don't have any thermal running in flow batteries. Most of the safety concerns actually come from the fact that we use electrolytes that are reactive. So they can be corrosive. So for example, vanadium oxide is a little bit corrosive, so it damages the pipes and the valves in the system. The iron flow battery is less corrosive than vanadium oxide, but again, it's a salt. So you can have salt deposition in the valves, which can block the pathways. However, to the best of our knowledge, the bromine-based electrolytes are the most corrosive ones. So the safety concern basically comes from the fact that if there is a leak and the electrolytes are spilled outside, then it can cause harm to whatever living being is around. So that is the basic safety concern for flow batteries. Next slide, please.
Let's actually pause
okay.
here, Prantik. There were a few questions that I want to just call out before you talk about long duration. One question here, maybe Elizabeth could be able to answer. The question goes, it looks like many of the deployments for these medium duration storage options align better with the short duration, so 2 to 8 hours categories. So can Black and Veatch, or I guess PSE, describe how these technologies were chosen as medium duration technologies? Is there a reason to believe that they are likely to have longer duration applications in the future? Go ahead, Elizabeth.
Yeah, so the short duration and medium duration actually overlap around that 8-hour mark. So we have short duration around, we said 2 to 8 hours, but it could be more like 2 to 6 hours, whereas the medium duration is 8 to 24 hours. And it's around that 8 hours. So these technologies do hit that 8-hour, which we've identified as the medium duration. For example, a lithium-ion battery we have as a short duration. It could be 2, 4, 6. It could even be 8 hours, depending on what the needs are, costs. And so this will all be weighed in with the needs, cost curves, and how these technologies can best fit. So we're just trying to categorize into the different topics, but some of these, correct, they can span both short and medium duration, depending on how we size them.
Thank you so much, Elizabeth. Let's have Prantik carry forward with 1 or 2 slides, and then we'll return to some questions in the queue.
Yeah, I'd like to add something to Elizabeth's point, and that's very valid, totally agree. The other thing is that whenever we consider any energy storage technology, we usually get a range of storage duration. And when we classify the medium duration or short duration, it's based on for what duration the levelized cost of energy comes out to be the lowest. So as Elizabeth mentioned, the lithium-ion battery can be deployed for 2 hours and 8 hours as well. But in the shorter durations, the levelized cost of energy comes out to be lower. So you will see like some overlaps. You see some overlaps for that reason, for between the short duration and medium duration.
Great.
So let's go ahead with the long duration energy storage system. Again, we are considering an electrochemical systems for that. So next slide, please. Okay. So for long duration energy storage system, for this project, we are considering more than a day, longer than a day, 24 hours of energy storage. And if you think about the utility of different storage durations, it's coming from basically from the fact that when the demand is high, like the short duration energy storage system satisfies the peak demand that happens, say, after the sun sets or before the sun rises, something like that. The long duration energy storage system, on the other hand, is meant for different applications. So there are some renewable, in some places in the world, the renewable power generation has an intermittency, which spans like over days. And so you need duration, you need energy storage that can store energy for days. And that's why the long duration energy storage system comes into play. However, one can also use those systems for backup power generation as well. As usual, we studied the different technical aspects of the 24 plus hours duration, and we only considered one technology for that, which is iron air battery provided by Form Energy for these 24-hour plus storage durations. Next slide, please. Okay, so right now, the main fact about, I think, the iron air battery is that it has got a huge footprint. It probably has the biggest footprint among all the energy storage systems. Right now, it's at TRL 7, so we are considering we are constructing a pilot scale project for this, and the pilot scale project actually got DOE funded, the 10 megawatt, 10-hour system in Colorado and Minnesota. And right now it is at a scale of like 10 megawatt, but definitely it can be scaled to 100 megawatts if needed. Next slide, please. So in terms of safety concerns, the only chemical that is corrosive in this system is the electrolyte, which is actually the regular electrolyte, like the normal electrolyte we find in like alkaline batteries, and it's basically potassium hydroxide. Besides this electrolyte, there is no corrosive element in this case, in this system. There are no thermal runaway hazard, so it doesn't really. There is not much fire concern. There is also very little risk of chemical spill or gas emissions because there is no thermal runaway in general. So in terms of safety, these batteries are definitely very safe. Can you go to the next slide, please?
I think that wraps us up, but we have some good questions in the queue. So yeah, stay on camera. The first question is, can you speak to the comparative efficiencies of these various battery systems and technologies? Like if 100% energy goes in, what percentage energy comes out? Which technologies in your mind have the highest losses or the best returns? Prantik, is that something that you can answer now, or do you want to put some answers into a feedback form?
I can answer it. I can answer for the electrochemical systems.
Yeah.
And I guess Mike can answer for the mechanical systems.
Great.
So among all the technologies, lithium-ion batteries have the highest efficiency. And the efficiency, the AC to AC round-trip efficiency, we have seen above 85%. In fact, in some cases, we have also seen close to 92%. So if you put in, say, 100 megawatt hour of energy into the battery, it'll get about, say, 90 megawatt hour back that way. The flow batteries, we have seen the round-trip efficiency in the range of 70 to 75%. Now, here is the thing. So the vanadium flow batteries have a higher round-trip efficiency. The iron and zinc bromide flow batteries have lower round-trip efficiency. With metal coordination complex, we are not so sure. We don't have much data until now. And the iron air battery, it actually suffers from a very low round-trip efficiency, and it's caused by the fact that there is an iron to rust and rust to iron chemical cycle that goes on, electrochemical cycle. And to the best of our knowledge, the round-trip efficiency for iron air battery, as of now, it's around 43%. So that is kind of like the range for the electrochemical systems. I guess those are the ones we covered. Oh, there is sodium sulfur. With sodium sulfur, it's a little bit tricky. If you don't have any source of external heat to raise the temperature to 300 degrees Celsius, we have seen sodium sulfur efficiency to be about close to 70%. However, if there is waste heat that can be used to raise up the temperature, then we have seen close to 80%, even like a little bit higher than 80% as well. So these are for the electrochemical systems.
Thank you for that. Mike, can you come back on camera and briefly answer for the mechanical systems? Keeping in mind we have a long queue of questions. Go ahead.
Okay, sure. Yeah, for example, the compressed air energy storage, an adiabatic type, could be 55% efficient. Maybe the range would be 45 to 70, and that's counting on if there's some additional waste heat. So it's going to be more 60 to 70 for that. For lathes, it's going to be 55%, with maybe the range 45 to 70. And then when you look at some of the gravity energy storage systems, they're going to be maybe in the 85+% efficiency. And just a side note on that, because they may not have an energy loss over the day, because you have raised the block up and you've held it there, you're not losing energy. So that has some advantage for that type of system.
Right. Thank you. Next question here is, Why is only one long duration technology considered? Consideration should also be given to hydrogen by electrolysis and tank storage, discharging back to grid using fuel cells. A study released in February by Mark Jacobson's group at Stanford shows that this technology is cost effective for long duration energy storage, 50 hours and greater. Is this a PSE? Do you want to respond to this, or is this a Prontic or Mike response?
Sorry, how to get everything on. I can take a quick response. So we are looking at hydrogen as a fuel source. So hydrogen through electrolysis or other forms. And what we're doing is pairing it with thermal peaking units. So yes, it can be used as storage. Yes, there are fuel cells. We haven't looked at the fuel cells. We're mostly looking at kind of a thermal peaking unit for this IRP process. And really with this long duration storage is as I mentioned, we're trying to get sizing. There are multiple different technologies out there. Iron air is a technology we're looking at for long duration, but we're just trying to get sizing and seeing how the long duration storage can kind of fit well into the portfolio and how it will work.
Thank you for that. Next question here is, and you might want to stay on, Elizabeth, has PSE considered the aggregate capacity of behind the meter BESS, which now I know means battery energy storage system, VPP, oh, you'll have to help me with that one, to serve some sort of short, medium, and even long duration storage functions. PSE, Elizabeth, have you considered this?
So I'm not as familiar with the virtual power plant technologies, but we'll see if maybe Malcolm can help answer that question when he goes through the vehicle to grid.
Great. So just hold on to that question, and Malcolm will be addressing this next. Another question here is, wouldn't some thermal storage fit under the long duration storage? And what are some technical and cost parameters along which iron air batteries need to still prove themselves for PSE to consider their large scale deployment? So let's start with the first one is, wouldn't some thermal storage fit under the long duration storage? Thoughts on that one?
Mike, would you like to go?
Sure.
I can give a very tentative. Oh, sorry, Mike, go ahead.
Yeah. So from a thermal energy storage, it certainly can be sized and appropriate for long duration energy storage.
Great.
So it would fit. Yes.
Okay. I'm noticing there's a lot of conversation about how do we categorize these.
Yes.
Yeah, so just keeping us moving. The second question is, what are some technical and cost parameters along which iron air batteries still need to prove themselves for PSE to consider their deployment? This is questions directed to PSE. So Elizabeth, any thoughts for that one or a feedback report?
Yeah, so our modeling process is what we'll be doing is the resources will be going in. And we do what is called a full capacity expansion. This is an optimization model in which it'll consider the operating characteristics of the resources, the cost of the resources, how it best fits into the portfolio. And what we're doing is going through an optimization of resources based on these cost characteristics and creating a portfolio, kind of a least reasonable cost portfolio, looking at all these different categories. So what goes in may not come out as results. We're just evaluating different options. This is not necessarily saying we're going to be doing these resources. Again, we're just trying to evaluate the options, and we'll be putting the costs in for evaluations as well.
Great. Thanks, Elizabeth. Two more questions before we'll actually turn to those virtual power plant and other topics here. So one is, NASA studied flywheel batteries in the 1980 to 1990 time period. What data do you have on that work? And I think this is a Black and Beach question. So Mike and Prontic, any familiarity with NASA's work with flywheel batteries?
Not in particular, no.
Okay.
I mean, there's a lot of other companies developing flywheel technologies now. Some are looking at, 4-hour discharge periods. So there's definitely development in it.
Great. Thanks for that, Mike. And the last question here is might be just a clarification on slide 35. So it's my understanding that the projects in Colorado and Minnesota are 100-hour batteries, not 10-hour batteries, as it says on slide 35. PSE, can you confirm that you're planning to model a 100-hour iron air battery and not a 10-hour battery?
Yeah, I think that was a typo. It's supposed to be 100-hour batteries.
Great. All right, good catch there. Okay, well, Black and Veatch, Prontek, and Mike, thank you so much for all of these insights and for all the participants for weighing in with your questions and comments here. I want to give Malcolm with PSE a chance to provide his insights, since I know many stakeholders are interested in these technologies. So Malcolm, please take us away.
Great, thank you very much, and excited to be here to talk to you all about the spotlight on vehicle to everything, which is more commonly known as V to X. And so with that, I'll just provide an overview of what that means, a little bit of detail on the configurations that are currently available and being developed, as well as what the readiness is of the market through those different transitions. And then finish up with talking about where PSE is developing some technology demonstration strategies and what the roadmap looks like for that deployment. And within that, I'll cover some of the questions, or at least talk about where the virtual power plant, or the VPP, gets integrated in that process. So next slide, please.
Jack, are you able to advance? There we go.
Great, thank you. So really, we've been hearing a lot about batteries, and the interesting thing here is with the rapid evolution of EV deployment within our service territory, we're going to have a lot more mobile batteries, and this provides a really great opportunity for the utility and customers to work in collaboration with each other to kind of take advantage of these two-way flow energy resources. And so as we think about the evolution of V to X, or vehicle to everything, the things that the PSE is really looking to understand and take advantage of in the demonstration process is to make sure that we can really identify and evaluate the technical feasibility, as well as the sort of operational requirements, as well as our own interconnection protocols to make these batteries more accessible. I'm then talking to our customers and making sure we understand, what it is that they conceive as the benefits and barriers to being part of this V to X experience. I mean, we know already from some of our research that, customers do look at this as an opportunity to use their vehicle as a source of backup power during outages. It also provides our commercial customers some opportunity for demand charge reduction. And then also thinking about opportunities for customers to earn from PSE when we want to leverage and use that EV battery for capacity needs. And that really, dovetails into where the benefits are for our system, and that is having additional resources, and more specifically, distribution level resources that we can leverage for capacity needs. And then evolution of additional use cases like load balancing and grid stability, and even looking at potential of deferral of distribution equipment upgrades if we see enough density of deployment in a certain area. Let's go to the next slide and talk about sort of what the configurations are available today. Many of you have seen advertisements of some of the electric truck makers that have the work crew outside of a home with their power tools plugged into the back of the truck. That was really the first use case, which is considered V to L, or vehicle to load. And that is currently available in a lot of forms today. What I'm going to be focusing on today is the two configurations that we're looking at, which is vehicle to home, or vehicle to building, as well as vehicle to grid. And the first use case is really being able to use that EV battery to provide supplemental power to the building. And some customers are using that as a backup for as I said, outage, but there are also instances that customers may be able to use that in the future as we deploy time of use rates more broadly to mitigate high cost during peak for their energy use. Vehicle to grid is a little bit more complex because it does result in actively injecting electricity right back into the grid. And so we do have interconnection protocols and approval and process that we need to put in place. So that is an understanding of what the sort of continuum is that is currently available. Next slide. So the market readiness, with anything, you have new technologies, there's sort of, current commercially viable and implementable capabilities, as well as, things that are moving on through the continuum of deployment. And currently, even though there's a lot of really good and exciting press coming out from a lot of different manufacturers, the availability of bidirectional vehicles and compatible chargers is still evolving and limited at this point. And that's partly because there's a lot of engagement happening to standardize protocols along, a variety of different market actors, including charging system producers as well as the vehicle manufacturers. And then we also need to understand sort of customer willingness to participate and have their vehicles used as a resource for the grid. Now, the good news is there is what is called V1G programs in market today. So PSE deployed its V1G or Flex EV product in March of this year. And what that does is it rewards customers for adjusting their electric vehicle charging on days when our demand or energy forecast to peak is high. And so we enroll customers either directly through the telematics on their vehicle or through smart or connected level 2 chargers. And this program is currently being run through our virtual power plant. So this is an area where we are currently accessing this load reduction capability through our virtual power plant. And we have about 700 customers currently enrolled through our demand response capabilities. But we will learn from that. But I think the main takeaway from the current market readiness is that that's still evolving. And the last point I wanted to make is that given the fact that this is not fully in the market today, there are higher incremental costs, not only for the equipment, being the vehicle and the charging equipment, but also for the interconnection process that needs to be refined through the utility. Next slide. So we are going to be going through a process of doing some technology demonstrations, and as I discussed earlier, really the outcomes is to make sure that we have the technical requirements, we understand how customers want to utilize this capability, how it will integrate with our virtual power plant, and also sort of the interactions that might happen between existing products and services we have in the market today, like demand response or time of use, or our commercial standalone battery or residential battery programs. So there's a lot we want to learn, and to be able to do that, we are looking to deploy some technology demonstrations. And really in these three main stacks, so vehicle to home, looking at about 10 installations where we can have a bidirectional EV that can be leveraged to help power that home, either in an outage or in the sense of helping with time of use. In vehicle to building, really looking at with deployment on the fleet side. And so this is where we would move towards a both level 2 and a fast charging facilities, and making sure that we could create that interconnection capability. And then lastly, vehicle to grid. And the use case that's most applicable today is with school districts and leveraging medium and heavy duty school buses. They have a duty cycle that is very defined, and they are also available usually throughout a summer period. And so really that's something that we are really excited about. And there are, I think, a lot of opportunities to test and make sure that technology, and most specifically the interoperability, we can do that in a way that's both reliable for our customers, but also safe for our system. Okay, last slide. We'll just talk through a bit about the roadmap and where we're going. So top of this slide, you'll see our standard product development process that we go through. And we're really sitting within sort of the design develop process or phase right now, as you see in Q2. Our intent is to move through the next steps defined here to really make sure that we've got our integration capabilities defined. We understand what tools and protocols we need to have, as well as making sure that we have the right technology partners, and then move towards identifying potential demonstration sites, conducting enrollment, so that we then hopefully can then start to dispatch these resources in 2025 during peak needs.
Great.
So I'll
Malcolm,
pause there. I see there's some questions that popped up. Yeah.
There are some good questions going on. So we'll take a few minutes to do that, making sure to leave enough time for public comment, maybe responding to that first question from Kara. So I think it was slide 39 here. There was a mention of an interconnection agreement. So would the interconnection agreement between PSE and each customer participating in the vehicle to grid, or would that be something else?
Yeah, so that interconnection agreement is basically our way to ensure that the energy, that the inverter involved in sort of that technology mitigates the backflow of energy onto our system without that direct control. So we will go through an interconnection process very similar to what we do with other renewable systems that come onto our system. And that's part of what we would be working through with this technology demonstration.
Great, thanks, Malcolm. The next question has to do with compensation. So the willingness of customers to participate in the vehicle to grid will be a function of how much they can earn. If they can reduce their electric bills by, say, $100 a month or more, you'll have a lot of people who are interested. Do you have any idea about the range of compensation at this point? Many customers will be interested in vehicle to home just to avoid power outages, of course. Thoughts, Malcolm?
Yeah, that great question. We have not aligned to what that compensation looks like, and that's part of that demonstration process and engagement with customers to really find out, there are a couple different things that we can learn from customers in this process of, to what state of charge are they willing to reduce their vehicle battery to, and what point of compensation are they really interested in. And so that demonstration will be part of that market research, and also looking at best practices from some of our peers who are also doing some demonstrations today.
Great. We're going to take two more questions. So is PSE concerned about the bottleneck of EV make and model compatibility with vehicle to everything equipment?
Well, that gets back to my comment of there's a lot of different approaches that are being assessed today, and there are OEM vehicle producers that are creating their own consortium of energy companies, and so that's part of what we need to understand and how to integrate those within our virtual power plant. But it is, again, that's why we believe that this is still a fairly nascent market, is because it's evolving. One example you can look at is, there are currently several different charging adapter standards that have been in place for many years for electric vehicles, and Tesla has now moved into being the standard that most folks are adopting. And so that evolution will happen normally as the market evolves, but it is something we're definitely going to be keeping an eye on.
Great. And last question for you, Malcolm. Does the operate phase of this roadmap indicate that PSE expects to open these vehicle to everything programs system-wide in 2025, or is that just the pilot or demonstrations that would come in then?
Yeah, so we will be demonstrating in 2025. That will provide us, again, with just the capability to really understand how we get these systems interconnected, and then we'll come back and move forward with broader deployment as we feel more confident about that technology or capability.
Great. Thanks so much, Malcolm, for that. We have one last question that I'm going to ask that we answer via the feedback form, just in the interest of time. Apologies, Matt, but there's a question just to read it aloud. Any indication that Tesla will get on the bi-directional bandwagon anytime soon? So we can use our PSE's best judgment then. So next slide, please, Jack. You have some next steps. Go ahead. Some additional resources for you. This is, again, in your slides available online and in the chat. Next slide. Dates to keep in mind, the feedback form for this webinar will close on the 30th. So if you have thoughts in response to Kara's initial question or any other questions or thoughts, you have until the 30th. The next public webinar is actually coming up pretty soon on May 9th, and this is going to be about local and regional delivery infrastructure needs. So it should be interesting. And then that resource planning advisory group that you've heard about, that on May 14th will have their meeting focused on the Western Resource Adequacy Program, or the WRAP. So with that, I'm going to ask Jack to stop sharing his slides and I can open up a timer here. And Emily, can I ask you to allow participants to raise their hands? Let's see my participant list here. Okay, I see a hand from Don Marsh. Let me just share my screen so that everyone can see the timer. Give me one moment here, share. All right, Don, I'm gonna allow you to talk. Let's see, can we hear you?
I hope so. Can
Yeah.
I come through? Great.
Please go ahead.
All right. Well, I just want to say I'm very happy to see a little bit of information about vehicle to everything. And if I had to choose just one thing that, if we could only do one of the things well that we heard about today, I think my vote would be on the vehicle to everything, because uh, the capacity of those batteries is going to be very big. It's going to be widely available throughout the service territory. It's going to be close to load. So that was, some of my concerns about the safety issues with some of the battery technologies. They're great if you can get them away from people, but people will be worried about having those installations in their neighborhoods. Whereas the vehicle to everything solution, the batteries are exactly where they need to be when there's power outages. They will increase the resiliency of our system. And also it could be an economical way to go, because a large part of the cost of those batteries is being borne by the customers themselves. So of course there's other equipment involved, but I think that's going to really become an interesting solution in the time frame of this the 20-year IRP period that we're looking at. I would be shocked if we're not seeing really robust participation in this in 5 years down the line or something like that. So thank you for letting me express those comments.
Thank you so much for your comments, Don. Let's see, anyone else? Scanning the room for anyone who wants to make a public comment. I put the questions posed in the beginning back in the chat. Emily, if I can ask you to put in the chat the feedback form link once again. Scanning the room. I'm not seeing any other hands at this moment. So I would actually, let's see, I don't want to break early just in case someone was going to come on for that last moment here. So we had the feedback form in there, and I'll just turn it over to PSE to say thank you and we can wrap up. Kara, can I turn to you just to close us out?
Sure. I just thank you very much for attending. I hope it was informative and interesting. And if you have feedback, the feedback form will be open for a while. So send us your thoughts. Thank you.
Great. Thank you all so much for the participants here today. And we hope to see you soon.